Hello everybody, welcome to Unit 9, Kinetics and Equilibrium. You should already have this document, but here's the breakdown. This is going to take us pretty much right up till spring break, so next Wednesday. So 6 lessons, kind of a short unit. Today we're going to look at Lesson 1, Enthalpy, right? Figure out what that is. Followed by some potential energy diagrams, entropy, reaction rates, equilibrium, and something called the Chatelier's principle. Okay, so we're going to dive right in here. Well, before I do, right, this unit is kind of focused on which way a reaction will occur, the energy changes involved in reactions, forward or reverse. It looks at rates of reactions, right? How do we speed up or slow down a reaction? There's multiple ways to do that. And then we'll end with talking about a little bit about equilibrium and the Chatelier's principle, which is a principle that talks about what happens when you stress a system. And by system, we mean a reaction at equilibrium. Okay, and we'll figure out what that is toward the end of this unit. So today we're looking at enthalpy, which is another way to think about it is called the heat of reaction. So its enthalpy is a measurement of the energy change during a chemical reaction. Okay, so in this first lesson, our intention is to calculate, represent, and explain energy transfer during a chemical reaction. All right, let's jump right in. So before we move further, right, a little review is necessary here. So take a minute, pause the video, go ahead and answer these two questions. Define exo and endothermic reactions, and then see if you can recall what unit we use for energy in chemistry. Okay, hopefully you paused and answered these two questions. So, quick review. In an exothermic reaction, right, exo is like exit, it comes out. Energy is leaving the reaction. So an exothermic reaction is going to make its surroundings increase temperature because energy is going to leave the reaction, leave the system, and enter the surroundings. So to us, an exothermic reaction would feel hot. An endothermic reaction is the opposite, right? Energy goes in, okay? So it's gonna suck heat away from its surroundings, and to us it would feel cold, right? Because it's absorbing that energy or that heat. And in chemistry, now there's a couple answers to number 2, but the unit we use mostly for energy is the joule, right? Capital J. I mean, you also see variations of the joule because it's a metric unit, so you might see kilojoule every once in a while. That's just 1,000 joules. You could use calories, right? We're going to focus mostly on joules, but you could use calories. That's also a unit of energy. Remember, there's two different measurements. There's two different calorie units, right? There's the little c calorie, and then there's the big C calorie. The big C calorie is what you see on food, and it's actually 1,000 little c calories. All right, so we're just going to use joules today, so we don't have to think about the two different types of calories. Okay, so enthalpy, what is it? Heat of reaction. So first, right, something that is key, is a key concept in chemistry. Systems in nature tend to undergo changes towards lower energy. All right, so reactions are favored when they release energy, right? Systems want to have low energy, so they tend to undergo changes that push them in a direction where they'll end up with lower energy states. So enthalpy, okay, also called heat of reaction, is the heat energy absorbed or released in a chemical reaction. Now look at the unit, delta H. You've seen delta before. You remember where? It was in when we were talking about energy as well. We were looking at, remember the equation Q equals mc delta T, right, for specific heat capacity? The delta means change in, right? So we used to use it that delta T was change in temperature. Well, here, delta H is change in enthalpy, right? You might have a positive change in enthalpy, a negative change in enthalpy. Okay, so let's see what those mean. So to calculate delta H, you take the enthalpy of the products and you subtract the enthalpy of the reactants. This is the same as the temperature, right? Final temperature minus initial temperature. right? Products are the final product. Reactants are what you start with. So it's final minus initial. It's the same, right? Products minus reactants. Okay. Table I in your reference table. We'll be looking at that today. That has the heats of reaction for a bunch of selected chemical reactions. We'll see that there's a whole list of reactions it gives, and it gives their enthalpy, their delta H. Okay. So let's take a look at this graphic here. Let's see what's going on. We got a balloon filled with, it looks like hydrogen and oxygen gas, right? H2 and O2, okay? Then it looks like there's a little bit of activation energy in the form of a candle. And then we see this explosion, right? When you ever have an explosion, right, remember that's heat and light being released to the surroundings. That indicates an exothermic reaction, right? Exothermic heat is very obviously coming out of this reaction, right? So what happens in this reaction, right? We have hydrogen and oxygen gas, both very flammable. They react, releasing heat and light in the form of an explosion, and turns into water, H2O. Okay. Over here, this little chart shows us the change in enthalpy, also known as delta H, for this reaction. Notice we're starting up here. These are our reactants, H2O2. Okay. Here's our product, H2O. There it is. So just judging from this graphic, will delta H be positive or negative for an exothermic reaction? Okay, so number one here, we're looking at an exothermic reaction, right? So if you look, okay, exothermic, the products end up with less energy than the reactants. And if we look at our little equation here, one way to think about it is delta H is products minus reactants. So if this is a lower number and this is a greater number, a small number minus a larger number is going to give us a negative number. Okay? So, right, we can see that we're ending up with less energy. So delta H will be negative for an exothermic reaction. Delta H will be negative for an exothermic reaction. That's very important to know, because then that way when you look at a delta H for an equation, you immediately know if it's exo or endothermic. So, as you might guess, number two here, delta H will be positive for an endothermic reaction. Okay? Now, this is super important. You might want to pause here and just really make sure you got this down, because it's going to help you out a lot later and the rest of this unit. So if you see a negative delta H, that's exothermic, right? Energy is released. That means the products have less energy than the reactants, okay? If you see a positive delta H, that means you got to put heat in, right? That's endothermic. That means whatever we end up with, our products are going to actually contain more energy than the reactants we started with, because they're absorbing energy. So negative delta H, exothermic. Positive delta H, endothermic. Okay? And remember, systems in nature tend to undergo changes toward lower energy. So what's favored by nature? Negative delta H. Right? Negative delta H means exothermic. That means our products have lower energy, and that's what systems in nature tend to change towards. So nature favors negative delta H reactions, or reactions that release energy, exothermic, where the products have less energy. Now let's look at a specific, well, actually this is the same equation as before. This is still the hydrogen, oxygen gas turning into water. What is the delta H for the formation of water vapor from hydrogen and oxygen gas? Now this is not something you're expected to know, but it is something you can look up, okay? So this is your reference table, well, one table of your reference tables, right? And you can see there's a whole bunch of reactions here. And in the right-hand column, it gives their delta H in kilojoules. Note the unit, right? So you'll see that some are negative. Those are all exothermic. Here's a positive, here's a positive. That means these two reactions are endothermic, right? So see how useful that positive negative is, right? Just by looking at the sign, right, I know, for example, this equation here, this reaction where nitrogen gas and hydrogen turns into NH3, it's negative delta H, therefore exothermic. I know that's going to release energy, okay? So we want to find this one, right? So you basically just look it up in the chart, and look at that. It's right here, I believe. Now careful, right? These two look very similar. The only difference is gaseous water or liquid water at the end. For us, it's gaseous, so we're looking at this equation. So the delta H for this reaction, right there, negative 483.6. All right? So that's just a matter of looking it up in the table. So make sure you can use this table, but be careful, right? These two are very similar. So we're looking at this one. So when hydrogen and oxygen gas combine to form water, gaseous water, it's exothermic, right? We knew that from the picture that is an explosion, right? But here's how exothermic, right? Here's a specific number. We're going to use these numbers in a second. Before we do, though, one other concept we got to think about, right? According to this chart, so I do want you to try this one. Just take a look at this chart here, okay? We have, it's a different reaction, okay? Doesn't really, notice how we don't really know what's the products, what's the reactants, right? Because it doesn't say if we're going this way or if we're going this way. It's showing us both, okay? But what we do know is higher enthalpy, lower enthalpy. So according to this chart, what can you say about a reaction and its reverse reaction in terms of enthalpy? Take a look at it. Pause if you need to. Okay, so hopefully you noticed that, right, the forward, let's say we're going this way, right? This is the forward reaction, right? I could have picked this one, doesn't matter. The forward reaction, negative 890 kilojoules. Now, when I reverse it, it's the exact same number of kilojoules, 890, but it's positive, right? So a reaction and its reverse reaction have the equal value of energy involved, but the sign is different. So when I take CH4 and oxygen, O2, and I use it to make carbon dioxide and water, this is a very simple combustion reaction, right? I release, so this is something this is a fuel source, this is burning methane. You burn methane, you get energy out, right? Negative delta H is exothermic. In this case, for every mole of methane, you get 890 kilojoules. And if I wanted to go backwards, right, I'd have to put in 890 kilojoules. Okay, so it's the same magnitude. The number's the same, but when you reverse a reaction, you just change the sign. Okay, so with that in mind, right, what's the delta H for the decomposition of water into hydrogen and oxygen gas? So this is the reverse of the reaction we looked at back here. Notice this reaction is nowhere to be found as it's written in our table. However, right, if we look, it's the same thing as this reaction, just backwards, right? We're going from 2H2O to making oxygen and hydrogen. That's what's happening here. So if you look here, this is the reverse reaction of the one we're talking about now. Therefore, like we just said in this last question, number 4, since if you reverse the reaction, all you do is change the sign in terms of enthalpy, we know that in this reaction, the delta H, it's not negative 483.6, it's positive 483.6 because it's the reverse reaction of what we see here. Okay, so a forward and reverse reaction have the same magnitude, the same number, right? They both have the 483.6. The signs are different, okay? Since the forward reaction, we'll call this one, is exothermic, it releases 483.6 kilojoules. The reverse reaction is endothermic, and it absorbs 483.6 kilojoules. All right, that's going to be super important because if you need to know the delta H of this reaction and you can't find it, you have to know that, oh, it's this one, but it's backwards, so I change the sign. Okay, if it's written just like it is here, you just take the exact sign and number. If it's backwards, you change the sign. Same number. All right, so how could we use this? How can we combine this with our stoichiometry we learned from the last unit? And remember, stoichiometry, very strange word. It's just talking about amounts of stuff, right? I have 10 grams of this. I put it through this reaction. How much of this do I get out? All right. Now we can also incorporate enthalpy in there, right? I have 10 grams of this. I put it through this reaction. How much energy do I get out or need to put in, depending on what type of reaction we're talking about? So here are the steps to calculating the heat released or absorbed in a chemical reaction. First, you have to add the heat term to the reaction, okay? If your delta H is negative, right, if heat is coming out, exothermic, then heat is a product and it goes on the product side of the reaction. If it's a positive delta H, which means endothermic, that means heat goes into the reaction and it goes on the reactant side. Okay, you need it. Reactants are things you need to start the reaction, right? In this case, you need energy. If it was endothermic, positive delta H, so the energy term would go on the reactant side. Then you convert grams to moles, right? Just like always. And then we convert moles to energy either released or absorbed. All right, so this will become more clear. Just 3 steps. It'll become more clear with an example. All right, so here's our example. How much heat is released? I'm going to start writing this on my paper. How much heat is released when 4.5 grams of methane, and that's CH4, methane is CH4, is burned. So how much, it wants to know how much heat is released. So it's saying heat is released, so we already know exothermic, okay? I'm just going to copy down this simple equation here so we can look at it together on my sheet. Okay, so we got methane combining with 2 moles of oxygen, making 1 mole of carbon dioxide and 2 moles of water. Okay, let's go over to the table. All right, this is what I got so far. So see, this is something you should do whenever you're doing one of these problems. I wrote down the given, and then this is going to be important, so I just copied it over. You won't normally have to do that because you'll be looking at the problem, but we want to keep this in mind. Okay, so remember, our first step was to add heat to the reaction. Okay, so I don't know what the delta H is for this, so I have to use my table. Oh, I should have done this a little better. So I have to find this reaction here in my table to know what the delta H is. So I'm looking for CH4. Oh, yep, look at that right up top. CH4, 2O2, makes carbon dioxide, 2 moles of water. So the delta H is equal to negative, and remember, it's just as it's written here, so it's keep the sign. So negative 890.4. Okay, and that's kilojoules. All right, so let's go back to our question. Okay, so I looked at my delta H for this reaction in table I. I wrote it down because I'm probably going to need it. So the first step was to include this term in the reaction, right? So this is negative delta H. This means it's exothermic. So when I'm including this energy term, an exothermic reaction, energy goes on the product side. Okay, so I'm going to actually rewrite this a little bit right above it to include it. I didn't give myself enough space. So we have methane, CH4, combining with 2 moles of oxygen to make, or to produce, or to yield 1 mole of CO2, 2 moles of H2O, and, right, and look, remember, this is negative. The negative sign tells me that it's exothermic. When I'm putting stuff in a reaction, never put negatives. It's always plus signs, right? So that's an easy mistake to make. So the negative just tells me it's going on the right side, on the product side of the equation. If that was positive, it would go over here. Negative, it goes on the product side. So plus 890.4 kilojoules of energy. Okay, so I'm just going to draw a line there. Okay, this is the one we care about. This is just some scratch work, right? I was just recording information. Okay, so we have 4.5 grams of CH4. Okay, first thing I want to do, well, second thing, right? Because I put my energy term in the equation, which is going to be important. Second thing, I'm converting to moles, right? You got to go through moles again. So what goes up must come down. Grams of CH4 comes down. I want to know how many moles of CH4 that is. Okay, so again, grams to moles, how do I know? I need to know the molar mass, which we get by adding up the masses of all the atoms in one of the compounds. right? So I'm going to do this quickly. If you remember, carbon's about 12, right? 12.011. Hydrogen's about 1. Realistically, it's like 1.008. So we have 12, 13, 14, 15, 16. So in 1 mole of CH4, we have about 16 grams of CH4. Okay? So that's going to get us to moles. Now, the last step, I'll make this a little longer. The last step, if we remember back here, right, look what I did. I added heat to the reaction. I converted grams to moles, right? Oh, I set it up. I haven't actually converted yet, right? I'm going to set the whole thing up. But if I solved this right now, I would have moles. Finally, I need to convert moles to energy. So if we look at our equation, okay, so again, what goes up must come down. So I know this is going to be moles of CH4, and I want to convert to kilojoules. Okay, this is the very new thing, right? So if we look at the equation, right, what's the coefficient in front of CH4? Well, it's a 1 because there's nothing there, so it's a 1. So if we put 1 mole of CH4 through this reaction, we get out 890.4 kilojoules. So the relationship there is 1 mole of CH4 in this reaction gets us 890.4 kilojoules. Okay? And now if you look, right, if I solve, right, I'm going to, grams will cancel here, moles will cancel here, and I'll be left with kilojoules, which is what I want my answer to be, because it asks, right, how much heat is released. Okay? So now, calculator time. I'm going to do the top first, right? So 4.5 times 1, so I don't do anything, times 890.4, right? That gets me 4006.8. I'm going to write that over here, 4006.8. And then across the bottom, that one's easy. 1 times 16 times 1, that's just 16. So I do 4006.8 divided by 16, and that gets me 250, and we'll call that 0.4. We'll do 1 decimal kilojoules. So here's my answer. So what we just did is we figured out if I take 4.5 grams of methane gas, natural gas, and I combust it, right? I set it on fire, basically. I combine it with oxygen to release carbon dioxide and water. I'll get 250.4 kilojoules of energy out of that. Now, maybe you see why this is important, right? This basically allows us to calculate the amount of energy we'll get from a fuel, from a specific amount of fuel. Now, you could do this with something like gasoline, right? You could take the incomplete combustion of gasoline equation and do the same thing and figure out how much energy you should get per whatever unit you want. You could say gallon. That'll be a hard equation to do, right? We don't use gallons in chemistry. So this basically lets us know we have this much fuel in this case, right? This is how much energy we'll get out of it. All right, so definitely replay that part of the video as I go through this process because it's brand new, it's confusing, but you do know a lot of the stuff already, right? The setup is the same. This is kind of the only new part, and this information comes directly from your equation. Okay. So once you've replayed that and you feel comfortable, go ahead and move on to the check your understanding questions. Okay, so go ahead and pause here. Okay. All right, so hopefully you paused and tried out these 3 questions. I'm going to do numbers 2 and 3 real quickly first, and then I will come back and do number 1 there. Okay, so number 2, a reaction is favored if delta H is what? So that's a weird question, favored. So when it asks that, what it means is favored in nature, favored by nature. And if you remember, the reactions that tend towards lower energy states are favored, right? So to have a lower energy, you must release energy. What type of reaction releases energy? Well, that's exothermic. And exothermic, what kind of sign does delta H have? That's a negative delta H. Okay, so a reaction is favored, right, by nature. It means it will happen spontaneously. It could happen spontaneously if delta H is negative. All right, that's going to be important later in this unit, okay? Because we're going to talk about another factor, because not always, right? Sometimes even a positive delta H reaction could occur naturally, and sometimes negative delta H reactions won't occur, even though it's favored by nature. Now, because there's other factors involved. All right, we'll talk about those later in the unit. Okay, number 3. Based on table I, right? Heat of reactions. All right, 101.3. Lots of numbers in there. We don't care, right? It says based on table I. The greatest amount of energy would be given off by the complete oxidation of 1 mole of. Okay, so that means I got to look at all my answers here. All right. So let's look at. We got C3H8. C3H8, 1 mole gives us. Ooh, that's a lot. This might be the answer. 2,219, basically. Okay. We got to compare them, though. We got to look at all our choices. CH4. Now we have CH4. And again, remember, don't be confused by the word oxidation. Notice they're all being combined with what? Oxygen. Okay. So CH4, right? We actually already looked at this. It releases 890. That's less. So I'm going to take that off. So right now, A is our best choice. C6H12O6, that's glucose. Let's look at that one. C6H12O6, there it is. Ooh, we have a new contender or whatever. 2,804. Okay, that's taking the lead right there. So glucose just took the lead with the highest. Right, it is asking for highest, right? Greatest amount of energy would be given off. Okay, so we're looking for the most negative delta H. And right now, that's glucose with negative 2804. Well, we got one more to look at. We got C2H5OH. That's ethanol. Okay, where's that? C2, oh, perfect, right here. Negative 1367. So our winner is glucose with negative 2,804 kilojoules being released per mole, right? Now notice, if these are all ones in front of these, right? If these were different numbers, we'd have to do a little math, but luckily they're not, so that makes it pretty easy for us. Okay, so the answer for 2 is B, and the answer for 3 is C. All right, and now number 1. Okay, this is like what we did in the the example problem. So we have a reaction, right? Which will, oh, look at that, it gave us the delta H. We don't even have to look it up. That's nice. So if 9.2 grams of NO2, so I'm going to write that down, 9.2 grams of NO2, put it over 1, multiply, okay, is produced, is heat absorbed or released? Oh, well, that's not even a math question yet. So if NO2 is produced, that's on the product side, which is what this reaction is telling us. Therefore, energy is released. Negative delta H. Look, negative delta H is exothermic. Exothermic means energy is released. So the first question is just asking us, is heat absorbed or released? Well, because this is negative, this is a negative delta H, and it's saying NO2 is produced, and that's a product, that means heat energy is going to be released, exothermic. How much? Well, now we got to do some math. Okay, so I wrote my given down. See, I wrote it there, okay? So first thing I want to do, right, is convert to moles and then convert to energy based on the equation, and I'll go back in a second here. So that's my given, my grams. So my next term, right, what goes up must come down, grams of NO2. I'm converting to moles of NO2, right? And I want to know how many grams are in 1 mole. To do that, I got to add up all the atoms, okay? So nitrogen's about 14. Each oxygen is about 16. So, and there's 2 of them though, right? So I'll do this one real quick, right? So NO2, we got 16 times 2 is 32, plus 14 gets us to 46. I think I did that right. So 46, right? 32, 14, yeah, 46. Okay, so there's 46 grams per mole, right? This will get us the number of moles of NO2, but we need one more step, right? What goes up must come down, moles of NO2, converting into kilojoules this time, right? Kilojoules. So again, now I need my equation for this piece. I don't just know that. So I look, I'll see that, ooh, okay, careful here. This is probably a place you made a mistake. Well, maybe, who knows? If you were to make a mistake, this is where it would probably happen. So look, in front of the NO2 in this equation, there's a 2. That means for every 2 moles of NO2 that are produced, we get 400 kilojoules out. So in my equation, I have to show that. I don't put a 1 down here because it's for every 2 moles of NO2, I get 400 kilojoules coming out of there. Okay? That's key. And remember, this comes right from the equation. Okay? 400 kilojoules, 2 moles of NO2. All right? Cool. And now this is, just the math part. We multiply everything across the top. We got 9.2 times 1 times 400. That gives us 3680. We're going to divide that by, 46 times 2. That's 92. Right? Well, 1 times 46 times 2, 92. So I do 3680 divided by 92, and that gives me 40 kilojoules. Right? Because if we look, those all cancel. We're left with kilojoules, so that's the unit of our answer. Okay? Definitely feel free to replay these. Some new math going on here. Homework tonight, right? Very similar to these types of questions. Hopefully, if you have any questions, right, bring them into office hours, either the day you're watching this or the next day. Okay? All right. See you guys later.